Hello and welcome to this clip on carboxylic acids and esters. We're going to cover the carboxyl group, the carboxylate ion, all about carboxylic acids, including how to test for them chemically in the lab, and a basic overview of the chemistry and uses surrounding esters. To top it off at the end, we'll do a worked exam question with a synoptic element to it that connects back to some Year 1 work that feeds quite well into this particular topic area. And throughout the clip, we'll assume that you're already comfortable with the chemistry of alcohols from your first year and carbonyl compounds, namely aldehydes and ketones, from the early part of your second year. Now, generally, the simplest way to make a carboxylic acid is to oxidize an aldehyde. The aldehyde themselves are produced by oxidation of primary alcohols. So hopefully all the stuff that's in front of you on the screen now is mainly a review from last year. The only slight difference might be the alternative oxidizing agent, which you don't really come across until your second year of A-level chemistry, which is potassium permanganate, or potassium manganate 7. That can be used too, and has exactly the same effect, although K2Cr2O7 is slightly more effective as an oxidizing agent in this particular case. In most cases we use potassium dichromate acidified, which is what we teach in our first year anyway for that reason. So carboxylic acids may contain a carbonyl group, which in this case is going to be the C double bond O. But they're not classed as true carbonyl compounds. And the reason for this is the presence of the second oxygen in the C single bond O actually is polar itself. So the C single bond O is also polar, as you can see from the dipoles. So that means that the original polarity, the distribution of electron density in the C double bond O is slightly different to, let's say, an aldehyde or a ketone, where you wouldn't have an electronegative atom attached to the carbon. In fact, what happens is you get electrons delocalized between two resonance structures in the carboxylate ion, so it sort of moves between the two in the same sort of way as the kekulé structure in a benzene ring, but only a little bit of delocalization takes place here. You can see the little dotted line in the blue structure. That shows a constant shifting back and forth of electron density between one carbon-oxygen bond and the other. So this is called resonance. It probably won't come up in any particular detail in any A-level question, but it's worth just pointing out in passing because it explains a little bit about why carboxylic acids don't behave as true carbonyl compounds. As you'd expect, carboxylic acids readily undergo hydrogen bonding, and this gives them certain properties. So, as you'd expect, they're soluble in water, and they're also more resistant to melting and boiling compared to other organic molecules of similar size. So it's the London forces and the hydrogen bonding that have to be overcome when you're melting or boiling carboxylic acids. However, as the size of the alkyl chain, in this case the R group, as that size gets bigger, this tendency diminishes and the influence of the hydrogen bonding starts to become replaced by the influence of the London forces, so they generally become less soluble in water. So there eventually reaches a point where they actually become of similar solubility to other similar sized molecules, organic molecules, and the effect of the hydrogen bonding is barely felt. And you always also include the carbon in the COOH group. So these four would be ethanoic acid, methanoic acid, butanoic acid and benzene carboxylic acid. You can see that I've highlighted the carbon chains that I need to use when I'm describing what the first part of the name is. They all end in oic acid, apart from benzene carboxylic acid. That one's a little bit of an anomaly. And quite often carboxylic acids play a role in our everyday lives that we're not aware of. I tried to look it up and find out what benzene carboxylic acid smelled like, because I've never been into contact with it, but I managed to find out that butanoic acid is actually very similar to the carboxylic acids found in human sweat, so smelly socks and old clothes, yum yum. Or butanoic acid Methanoic acid is the active ingredient in ant stings, and ethanoic acid, you probably know already, is part of vinegar. So there's actually a range of reactions that carboxylic acids undergo that you need to remember. The key thing to have a look at is that there's a metal carboxylate salt produced in each reaction. There's one particular reaction down at the bottom of the screen, which is a lab test for carboxylic acids. The reaction of carboxylic acids with carbonates, metal carbonates, causes fizzing, and that can be viewed as effervescence. So that can be a diagnostic test for the presence of a carboxylic acid. So the key things to remember: carboxylate salt, the metal is made in each case. It's highlighted in black or named in black to make it clear here. And also watch out for mole ratios depending on the charge of the metal ion. I've mixed and matched my metals here a little bit so you can see that in action. So with magnesium and calcium, for example, those are 2+ metals. So notice that the metal carboxylate salts have 2 carboxylate ions to 1 metal. It's a very easy one to miss, and people often miss it out in equations. And people who otherwise understand what they're doing actually end up losing the mark for such a silly reason as that. So do look out for that in exam questions, because they seem to like putting that in. So let's now have a look at esters. Before we go on to do that, I just forgot to mention that the reaction of metals with carboxylic acids is a redox reaction, as opposed to the other ones, which are not. So the other ones are acid-base reactions, and the one with magnesium reacting with methanoic acid is a redox reaction. So metals reacting with carboxylic acids are redox reactions. So esters don't hydrogen bond quite as easily as carboxylic acids due to the absence of the hydrogen atom attached to the oxygen. So as such, they're not quite as soluble. So what you need to do to make an ester is to reflux an alcohol and a carboxylic acid together in the presence of a strong dehydrating agent such as sulfuric acid. Because it's a reversible reaction, the acid must be concentrated to try and drive the equilibrium as much as possible to the right, favouring the production of the ester and maximising its yield. Highlighted in blue is the ester functional group, and highlighted in green is the source of the water molecule that's produced as a side product. So some of the water comes from the carboxylic acid, some of the water comes from the alcohol. And it's also important to remember that the acid also has a role of catalyst. The exact mechanism through which it does this is rather complicated, so it's not included in your A-level syllabus. But an understanding, or at least an appreciation of the fact that the acid catalyzes the reaction is important. So we've got another example of preparing an ester by reaction of an alcohol with a carboxylic acid. We can also do the same thing using an anhydride. Anhydrides are more reactive than carboxylic acids, so they tend to do the reaction a lot easier, and they don't need to be refluxed or react with a strong acid. So sometimes this is done to make the reaction go quicker, although anhydrides are more dangerous than carboxylic acids to deal with. So it swings in roundabouts. So you get a faster reaction, but you have a little bit of extra health and safety to bear in mind when handling acid anhydrides compared to carboxylic acids. So when you're naming esters, what you've got to think about is what is the alcohol and what is the carboxylic acid that were reacted together. So in these instances I've colour-coded it, and the first part of the name comes from the alcohol, so the ethyl or propyl or methyl or propyl, whatever. And the second part, the part that ends in O8, comes from the carboxylic acid. So it's always yl and then anoate. So methyl butanoate, for example. So esters are commonly found as fragrances and flavours. It's a common use of them. They're found in nature, in flowers, the fragrance of flowers, in fruits, and vegetables, and they're also used in food flavourings to impart certain flavours to foods that we cook. So things like chocolate, cheese flavours, all sorts of flavours, usually can be traced back to esters. So esters have several different common uses. The most common one you may not have realised is ethyl-ethanoate in nail polish remover. In the last screen it mentioned pentyl-ethanoate in bananas, and in many fragrances such as perfumes and deodorants you get phenyl benzoate. And the skeletal structures are as shown. So let's have a look at some of the reactions of esters. Esters can be broken up by hydrolysis, which is basically the use of either water or an OH- ion. In this case, with an alkaline hydrolysis, you're using an OH- ion to break up the ester into a salt and an alcohol. So with acid hydrolysis, the acid behaves as a catalyst, and it's the water that's causing the hydrolysis to happen. And you get a carboxylic acid and an alcohol back. So I've added some key points here in blue for each reaction that you might want to pop down in your notes if you haven't done so already. There are slight differences between the two hydrolyses, so it's important to make sure that you're familiar with them, not just the reactions themselves. One thing to definitely have a look out for in exam questions is cyclic esters. If we take this example, you've got two functional groups on the same molecule. One is a carboxylic acid group and one is an alcohol. And not surprisingly, if you reflux that compound, those two functional groups will react with each other. You end up getting a cyclic ester. So if we just track what's ending up where, you can see where the H2O came from, and you can construct in your mind what the product will look like. They will throw things like this at you in exams, so do watch out for it. Provided you can visualise that OH comes off the carboxylic acid and H comes off the alcohol, you can remove those three atoms to make water, and then the remainder will join up to make your ester. Right, so let's have a look at a typical exam question. You can see straight away that it says compounds and structures here that you probably haven't seen in a textbook. That would be deliberate in any examination. So it's obviously got an applied element to it. And it's a very common way of testing out your ability to deduce organic syntheses and organic synthetic pathways by naming compounds as E or F or A or B or C, for example. So the information they do give you is that compound E is an alcohol. You can clearly see that. It's got two alcohol groups, one secondary and one primary. So let's just put that down straight away. So it's always a good idea, as you go through these papers, these questions, as you spot something, excuse me, it's always a good idea to try and label it or make a little note to yourself. There's nothing wrong with doing that. The examiner won't penalise you for doing that. In fact, it's going to help you think your way through the question. So then it says compound E can be converted into compound G as shown in the flowchart below. What I'm going to need to do is to bring the page down a little bit so you can see the full flowchart. Okay, so compound G is this one down at the bottom. And you can see quite clearly that what you have is a carboxylic acid on one end of the molecule and a secondary alcohol group elsewhere in the molecule. So what we can do is pull the page down a bit to see what it's asking you. It says complete the flowchart to show the structure of the compound F and the reagent needed for reaction 2. So looking at compound E in reaction 1, you're going to reflux it with excess K2Cr2O7 in the presence of an acid. So in other words, you've got an oxidizing agent. You've got two possible things that could be oxidized here. You've got your two alcohol groups. Each of those will form a slightly different oxidation product because one's secondary and one's primary. So as you'll recall from your work on oxidation of alcohols in your first year, the primary alcohol will oxidize to a carboxylic acid, this, and the secondary alcohol will oxidize to a ketone, like that. So, next thing to do is to look at what changes from compound F to compound G. So if we look closely, you can see that in compound F, your ketone gets changed back into a secondary alcohol. So in order to achieve this reduction, obviously you would need NaBH4. This would be from your earlier work on carbonyls. This is pulling in a little bit of alcohols and carbonyls from both years of the A-level course. So it's always a good idea to quote that it's NaBH4 in aqueous solution, because the water in the aqueous solution also gets involved in the nucleophilic addition mechanism, if you remember. So let's move the page down a little bit. There's nothing more on that page, so we can go straight on to the next screen. Now it says, what would you observe during reaction 1? So if we remember, reaction 1 was an oxidation. So in the absence of being able to go back to the page, you'd normally be able to flick the page back and just put a little reminder at the top that reaction 1 was an oxidation using K2Cr2O7 in the presence of H2SO4. You'll probably recall from your first year work on alcohols that you'd see a colour change from orange to green. Then it asks you to suggest why the refluxing conditions were used instead of being distilled. So again, a bit of first year chemistry here, ensuring the primary alcohol is fully oxidised to a carboxylic acid, as opposed to the alternative, which would be partial oxidation to an aldehyde. So the type of reaction taking place in reaction 2. Now we said it was a reduction, but they probably want to know the mechanism. I know they haven't said the word mechanism, but try and give as much detail as you can here, even though it's only 1 mark. So I've put a little exam question technique hint at the left there. It's obviously an A2 question, so if you're able to talk about something like nucleophilic addition, go that further step and say nucleophilic addition. I've put reduction in brackets because technically it is a reduction. We'd probably allow that, but at the same time, the best way of answering this bit would be to call it nucleophilic addition. Obviously, you'd be using NaBH4, like we've just said. That is used in reduction of ketones, for example, and therefore, as such, it's a nucleophilic addition mechanism. The next one is simple recall. It's simply remembering that we use 2,4-DNP to test for the presence of carbonyl groups, and we look for an orange precipitate, so that would be the 2 things you need to say there. So bringing the page down slightly, this part of the question is really only to be attempted if you've done some work on stereoisomers. So let's remind ourselves what compound E actually is. So the type of stereoisomerism that they're talking about here is something called optical isomerism. And when you first come across carbonyls, you won't have come across optical isomerism yet, so it depends on what stage in the year you're listening to this video clip. Just very, very briefly, all that optical isomerism means is that a carbon atom in a structure has to have 4 different things coming off it. So in a nutshell, I'm doing this assuming you haven't done optical isomerism yet, the way you spot optical isomerism is by looking for a carbon atom where there are 4 different groups attached directly to that carbon atom, and therefore there could be mirror images of that setup. Let me try and explain what I mean here. So you'd have optical isomer 1 and optical isomer 2. Now I don't want to go into the sort of detail of what actually happens. It's to do with the rotation of plane polarized light, which is something that we'll cover separately when we teach optical isomerism in greater depth. But for the time being, all you have to be able to do is spot this effect where there's a mirror image, possibly. So this compound E, what the question is telling you, it's saying that there is one other stereoisomer of compound E. So we've already got the type of stereoisomerism, we can call it optical isomerism. So remembering that skeletal formulae don't actually show hydrogen atoms unless they're part of a functional group. If you look at where I've highlighted in dark grey, those are the 2 places where this effect will occur. So the kind of thing you'd need to put down would look something like this. So I've drawn in the 2 stereoisomers, and use the dark grey highlighting to highlight the carbon in each case where stereoisomerism is occurring, optical isomerism is occurring. So like I said a couple of minutes ago, depending on where you are in the course, if you're watching this for the first time and you haven't done stereoisomerism and optical isomerism yet, don't worry too much, it will be covered. If you're watching this as a review, the idea of optical isomerism should be fairly familiar to you and should be quite easy to follow. So I'm trying to make the clip fit whichever position you're in. Okay, so now let's have a look at the next page of the question. So this part of the question is a calculation. So what I've done to save having to sort of flick back through the screens, I've put compound E and compound G together because on the first page of the question that's where you had to work out the reaction conditions for conversion of compound compound E into compound G. So it says the MR of compound E is 160, and you can also see quite clearly there's a 1:1 mole ratio. So what you need to do is convert the masses into moles. So we can straight away work out that the moles of E that were used are 4.56 over 160. In other words, mass over MR. And knowing we'll have to do the same thing for G, we need to work out the MR of G. So I've calculated that as 174. So now I can do the same calculation for G that I did for E. So because it's a 1:1 mole ratio, you'd expect, given 100% yield, for 0.0285 moles of G to be formed. As you can see, there's a lot less than that. It's 0.0181. So that gives us 63.5%. So moving the whole page down a bit, final part of the question. It says compound G is heated for several hours under reflux in the presence of a concentrated sulfuric acid catalyst. An ester and a small inorganic molecule are formed. So this tells us very clearly that we're dealing with an esterification. So that means that these functional groups will react with each other. So it's another example of a cyclic ester that we talked about a little bit earlier. So it's another cyclic ester, like I said. So that would be the kind of thing you'd be hoping to put together for this last part of the question. So let's now have a quick look at the mark scheme. Right at the beginning, we got F and we got our reagent, both for 1 mark. And we got our correct colour change, orange to green. And we talked about ensuring that carboxylic acid is formed and prevents formation of an aldehyde, both points needed really to secure that point. Nucleophilic addition is ideally, like I said, what they'd want you to put. They allow you to do redux or reduction, but the slight problem here is they might not allow it every single year. It might be just a bit of generosity in this particular year. So don't rely too much on that same level of generosity and leniency in other questions. We said it was 2,4-DNP, didn't we? That it was the reagent that was used to test for carbonyls, and we're looking for an orange precipitate. So that was that page sorted. Those are the possible options we could choose from for our optical isomerism. Again, I'll just reiterate, if you're watching this video clip early in the A2 year and haven't covered optical isomerism yet, don't worry too much. But if you're watching it later in the year, once you have covered optical isomerism, this will make a lot more sense to you. So in our calculation, if we got 63.5%, that would get 3 marks straight away. But it's always a good idea to make sure we put in our workings so you can see where the ticks are awarded. If the final answer isn't actually 63.5, at least you might get some method marks for putting in your working. And finally, we get our cyclic ester and H2O produced. So it's always worth taking a moment to just have a quick look at how the wedges and the dashes are used to show the three-dimensional structure of a molecule. You've got to make sure that the wedges and the dashes are the correct orientation. And again, if you're not used to optical isomerism and haven't gone too deeply into the A2 year yet, this will come when we cover it in our lessons with you. But if you're towards the end of your A2 year, you'll no doubt by this stage be quite competent and comfortable with using dashes and wedges to signify the three-dimensional nature of molecules. So hopefully this is a reasonably useful clip in introducing you to carboxylic acids and esters and showing you how you can apply knowledge of them and knowledge from your S year, your first year, to a fairly applied sort of exam style question. So if you have any queries, then come and see one of us in college in a subject extension or have a chat to your teacher. But in the meantime, thanks for your time and see you soon.